Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jumana Tariq Nabil Abdurazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Engineer Maria Leticia Vazquez, a very special guest from Mexico. Engineer Maria has a BSc in mechanical engineering and has been working in Schlumberger for 19 years within the wireline organization. Maria has performed 3 different major roles in the wireline cased hole business in Egypt, Oman, Scotland, and Sudan, a field engineer, cased hole logging instructor, and domain champion for well integrity, production logging, and perforation. And today she will be sharing with us her expert opinion on production logging tools. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask you to give your full attention to Engineer Maria and help me in welcoming her. Please welcome Engineer Maria. Hi, Engineer Maria. Thanks for joining us today.
Thank you very much for the great invitation. So my name is Maria Vazquez, and today we are going to talk about production logging. And basically, production logging, something that we have to consider is that it is a wellbore measurement in general. And the most important part about production logging is to understand how much is my well delivering, from where is coming the oil, from where is coming the water, from where is coming the gas into the wellbore. So as you can see over here in the picture that you have in the slide, the first thing that we have is here, you can see is 2 wells. In the well in the left, we see that there is water production from the zone number 3, from the most bottom perforation, P3. And then we have that zone number 2, P2, is taking some of this water. And this can happen because the pressure in the zone number 3 is higher than the pressure in the zone number 2. And then we see that some of the water is being produced, and zone number 1 is basically producing only hydrocarbon. So this is one of the type of problems that we would like to identify with production logging. In the well in the right, we can see that there is a poor cement behind the casing. So we can see that the water is going through the channeling, through the cement. And even though our zone is just hydrocarbon bearing, we have actually water entry due to the poor cement in behind the casing. So this is what we call water production through channeling. And of course, that is going to affect the performance of the well. So basically, this is just a brief introduction, but why is production logging performed? So again, as I mentioned before, we need to know how much of what is coming from where. So basically, we are going to measure the parameters of the well zone by zone to be able to understand how the fluids are moving in the wellbore. We can also see to some extent, movement of fluids behind the casing, but our main interest is going to be the wellbore. So over here in this picture that I have in this slide, we can see the Schlumberger truck or any truck from any service company. And we see over here the rig up on the wellhead, yeah? In this case, this is the Christmas tree. Most of the production logging surveys are done rigless, meaning that the rig is not in place, yeah? We also do surveys with the rig in place, but most of this kind of work is done rigless and already with the completion in place. So you will have over here the Christmas tree, yeah? And then you lower your production tool with the wireline cable, and you can actually see over here every zone, how much is every zone producing, yeah? So basically, this is the idea, to understand how much of what is coming from where. And we can see over here just a small example of the measurements that are done, but we will describe one by one all these measurements. So talking about problems that production logging can identify, so the main core of production logging will be, number 1, evaluation. So we want to see the production profile distribution and the zonal productivity. This could be even a baseline log. Once you have already your completion in place, and you already, or even along with the testing, you can actually do production logging and understand the status of the well when the well is actually new, yeah? And understand which zones are producing, which type of fluids are entering from every zone. So this will be for evaluation. Next step will be monitoring. So with the time, also the production profile is going to change. Many times we do production logging several times through the history of the well to understand how the production profile is changing, and also to understand if there is any remedial that we should do to be able to stop producing unwanted fluids. This could be water or this could be gas. So we can identify water breakthrough, gas breakthrough, in case we don't want to produce gas, for example, but we want only to produce oil. And also for diagnosis. So basically, what is the zone of a high GOR or a high water cut? And also to detect if we have presence of cross flow. We can see over here in the picture that is on my down right side, you can see the example, for example, of a thief zone. So thief zone, again, is whenever the pressure of one of the zones is higher than the pressure of the other zone, and then the fluid is being taken by the zone with low pressure. And so this is also what we call cross flow. Also, whenever we want to do any production enhancement, so to be able to understand some data, to be able to enhance, to plan for our workover, to be able to plan for any change in completion as well, because sometimes we have leaks. So for example, in the top left side, we can see the example of a packer leak, and we can see also a leak in the tubing. So these are things that we would like to understand to see what will be the remedial to be applied. For example, we might need to retrieve the completion and be able to change this tubing that is having leak, that is having already holes, by a new completion, yeah? And also the packer. So it can also help us to understand the status of the well and plan for workover operations. So now we are going to see which are the sensors that are available typically in a production logging string. Okay, so which are our needs in production logging? Our needs are to understand quantity of oil, quantity of gas, and quantity of water. And we know that the flow rate is equal to velocity times area. And the measurements that we would like to do are the velocity of fluid. How are we going to measure the velocity of the fluid? We will do that with what we call a spinner. So you also will hear the name as flow meter. And another way of understanding the velocity of fluid can be through a nuclear measurement called water flow log. We need to know the diameter of the casing, because at the end of the day, we say that flow rate is equal to velocity times area. So the diameter of the casing, we can know it by a caliper. So we can have in our production logging string a caliper. Hold up, we can measure it with different type of sensors. One of them will be the density sensor. We have in a Schlumberger also what we call the electrical probe, and we have also a gas hold-up sensor called the optical probe. If we need to measure temperature, we have an RTD, and if we want to measure pressure, we can do it with a pressure gauge, some sapphire gauge or quartz gauge. So over here, I have a picture of the production logging sensors. And we can see over here the basic sensor that contains typically temperature, pressure, gamma ray, and CCL for correlation. And we can see over here the spinner flow meter. This is what we call a full bore spinner, yeah? So the spinner is basically enclosed in a cage. In this case, this cage is also going to act as a caliper. And we can see over here the electrical probe. The electrical probe will help us to understand the water hold-up presence. We can see the optical probe that will help us to understand the gas hold-up presence. We have the Gradiomanometer tool that will measure the wellbore fluid density, And we have as well nuclear tools that could help us to understand saturation and also water movement, what we call the water flow log measurement. Yeah. Now the very basic PLT string will be the pressure, temperature, gamma ray CCL, spinner, and caliper. This will be our very basic PLT string. Now, production logging is not done in the same way any other logging is performed. Normally, whenever you log, you go down to your target bottom log interval, and then you go up by recording whatever you need to record, okay? In production logging, the program is a little bit different. So basically, the production logging program typically, there might be variations to this, but typically is divided in shutting condition and flowing condition. So in shutting condition, the well is static. And what we are going to do is that we are going to perform several passes at different speeds. And we have to maintain through the logging interval the speed constant. This is to be able to perform what we call a spinner calibration. Now, the spinner, whenever it provides the measurement, the spinner is going to provide the measurement in RPS, revolutions per second. The spinner rotates. But in reality, I do not need revolutions per second. I need a linear velocity. So the spinner calibration will help me to translate that rotational velocity into a linear velocity. And at the end of the day, what we are going to obtain, or what we need to obtain, is the velocity of the flow. Then the shutting condition also helps us to determine fluid levels. So for example, where are the segregation between water, oil, gas in the wellbore? And also is going to be the main condition in which we can detect cross flow. So for example, we can detect if a pressure zone is what I mentioned before, a zone that is having a higher pressure that is feeding into a zone with lower pressure. Also, that is going to be mainly observed in the shutting condition. Now, once we open the well to production, we need to wait for the flow to be a stable flow. Typically, we understand that by looking at our pressure sensor. Also the spinner temperature density, we see that our pressure is constant, and then we can start to perform passes, up and down passes at different speeds across the logging interval. And in this case also the purpose of these passes is to identify the flow profile, to identify the fluid entries, and again also to help us with the spinner calibration. And typically we also do stations, and these stations are very important because they will confirm whenever there is a flow coming from a particular zone, it is going to be a confirmation, yeah? We can see over here the well, how it's producing, yeah? So now, for production logging interpretation, what are the facts? So what are the things that we can determine and interpret? If I have a single phase scenario, I can determine the downhole profile, and the interpretation is really straightforward. I just need my spinner, I just need pressure, temperature, gamma ray, and CCL for that. If I have a multiphase flow, meaning I have oil produced with water, or I have gas produced with oil, or I have gas, water, and oil, the three of them produced at the same time, then we need also this interpretation, we will need to know the hold, basically. So how much space is going to be occupied by every phase in the wellbore. And we also need to determine something called a slippage velocity. So all this will complicate the way the spinner is going to rotate. So it's very important that we have hold-up sensors in this case, and our interpretation model will have what we call a slippage correlations that will help us to be able to reach a conclusion. So the hold-up is basically a major importance in the multi-phase flow production logging interpretation. Now, something that is very important, and we insist a lot to our customers whenever we are going to plan for a production logging job, is that they provide us as accurate as possible PVT data. And the reason is because some failures to provide an accurate PVT data can induce errors in the calculations that are going to be done by the production logging and in the interpretation. Now, something that can reduce the error of inaccuracy on the PVT data is to have hold-up sensors that can directly measure the hold-up of water and the hold-up of gas. But if we are going to work traditionally with a density measurement like the Gradiomanometer tool, it is very important that we know accurately the downhole density of every phase. It is something important for the proper and accurate interpretation of the production logging log. Okay, so for example, when I have my electrical probe or my optical probe that identifies the water holdup and the gas holdup, then I can eliminate many of the errors that are induced by the PVT data in the interpretation. Now, we are going to talk a little bit very basic understanding on flow regimes. So flow regimes, typically, we will have what we call the laminar flow, and we will have the turbulent flow. And how are we going to define laminar flow to from turbulent flow? In this case, for example, in the laminar flow, something that we have to understand is that the spinner is actually centralized in the casing, yeah? So the spinner is centralized in the casing, so if I am in the presence of a laminar flow, I will have the spinner reading maximum velocity. And in laminar flow, velocity average, which is what I actually would like to measure, is equal to the velocity maximum divided by 2, okay? This is in the case of laminar flow, but in reality, in oil field, we don't really deal with laminar flow. We deal with turbulent and transition flow. We don't deal really with the laminar flow. So in the case of turbulent flow, the velocity average, okay, is the relationship between the velocity maximum and the velocity average is going to be given by something called velocity profile correction factor. Now, how we know that the flow is going to be laminar or turbulent? This is based on something called Reynolds number, okay? Whenever Reynolds number is less than 2000, then this is considered as laminar flow. Whenever the Reynolds number is more than 2000, we consider this as a turbulent flow. And again, polyphasic flow is always turbulent or transition. So the inputs to Reynolds number, things that we have to consider, and that are inputs to Reynolds number, is going to be, number one, the diameter of the pipe, the fluid velocity, the fluid density, and the fluid viscosity, yeah? So our velocity profile correction factor at the end is dependent on the Reynolds number, and the input of these values is actually need to be correct. Now, we are typically, whenever I give this presentation, we do an spinner exercise, but in this case, we don't really have time for the spinner exercise. What we are going to do, I will explain to you now about the spinner sensor itself. So, as you can see over here, the spinner is centralized, okay? We have basically the caliper is going to help us to measure the area, or basically measure the diameter, and then we will be able to calculate the area. And then we have the spinner that at the end of the day, our output that we require is the velocity of the mixture. But as I said, our final answer that we want is the flow rate. And for that, we need the velocity of the mixture in a linear velocity, not in a rotational velocity. And the spinner, as you can see, is always to be centralized inside the casing. Now, something here that we have whenever we look at the spinner response, we are going to be in the presence of two factors, two variables. Number one, the velocity of the flow, and number two, the velocity of the cable. Because the passes that we are going to be doing up and down at different cable speeds, we are going to basically be moving the tool, we are going to be moving the cable, but at the same time, we have the velocity of the flow, either if it is injection or if it is production. So basically, at the end, what we want to understand is the relative fluid velocity to tool velocity. So we can see over here how whenever I take all my passes, all my up and down passes, what we do is that we merge these passes into a format, yeah? So basically into a picture in this case. So this is the log, this is a representation of the production log, the spinner in this case. So you can see in the left side the different cable velocities. And something very important is that we should always keep the cable velocity constant. Then this shaded area is the perforation. And then on the left side, you will see the spinner response in RPS, revolution per second. So below the perforation, nothing is moving. I have no flow coming from below the perforation unless I have old perforations that have been isolated by a plug, for example, and are leaking, and the plug is leaking. In this case, let's say that there is no leak of any kind, and I have just this perforation zone, and there is no flow coming from the bottom. So the first zone highlighted in purple in the bottom is what I will call zero flow region. No flow is making the spinner rotate. In this case, in zero flow region, all the rotation of the spinner is dependent on the cable velocity. Then I see that over here my spinner is increasing in magnitude. This is because now I have production entering from the perforation. I have flow entering from the perforation. My perforation is producing. So in this case, I have the cable velocity plus the velocity of the flow that is entering inside the wellbore through the perforation. And then at the top region, I will also select a zone in purple as well, and this will be my flow region, okay? So like this, we can understand basically what is a zero flow region and what is a flowing region, okay? And again, cable speed is very important to maintain constant. Whenever I merge my passes, my spinner response has to be repeating. So for example, I should not have a different shape from one pass to another pass. This is part of the quality control that we need to do to the spinner passes. The shape of our spinner passes have to be the same, independent on the velocity at which we are acquiring them. Now, a convention in production logging, whenever you are either a logging engineer or an interpreter. So for us, positive cable velocity is going to be given whenever you are going down, you are making a down pass. So how we actually consider it or memorize it is we consider that whenever you are going down, your depth is increasing, yeah? So then the velocity of the spinner, the rotational velocity of the spinner, we consider it positive. Let's say that the well is in a static condition, there is no production, there is no fluid movement, but I am just moving the cable and I am going down. When I am going down with the cable in a static condition, with the well in a static condition, only moving the cable, my spinner is going to be rotating with a positive sign. Now, let's say I'm going up, also the well is completely static condition. I am not having any production or injection, no dynamics. I am just moving the cable up. My spinner in this case is going to be rotating negative. So we have that the spinner, the sensor in the spinner can tell us, okay, a spinner is rotating positive or a spinner is rotating negative. Now, consider that I am having a perforation that is producing and I am not moving the cable at all. Any fluid that is coming from bottom to top, in this case production, for example, is going to make the spinner rotate positive. And whenever I have any fluid coming from top to bottom, for example, in the case of injectors, wells, in the case of injection, the spinner is going to be rotating negative. So, for example, let's say I have a producer well, and I am moving my cable down. Whenever I am below the perforation, the spinner is going to be rotating positive, but whenever I am in front of the producing zone, my spinner is going to rotate now more positive, okay? Because production makes the spinner rotate positive and moving the cable downwards makes the spinner to rotate positive. Okay, now, whenever we are going to do the spinner calibration, basically those passes that you saw, we are going to plot them together, okay? We are going to have here the tool velocity and we are going to have here the spinner RPS. So these points, these green points that you see in this plot are basically The tool velocity, let's say I am moving my cable at 30 feet per minute. What is the RPS that I was reading when moving the cable at 30 feet per minute? And I will actually plot my point. Then I was moving the cable at, let's consider this, that this is the zero flow zone that we saw in the previous slide, yeah? I am moving my cable at 60 feet per minute. So what is the RPS that my spinner is reading at 60 feet per minute? And so on, with all the different cable velocities. And then we are going to trace, or the software actually, or you can do it by hand, we will trace here a best fit calibration line. Now, in reality, okay, if we were having an instrument that doesn't suffer from friction, okay, our line should start from 0, but in reality, the spinner is a mechanical instrument that will suffer from friction. The spinner will not start to rotate immediately. It will rotate with certain, when exposed to certain flow, certain amount of flow or velocity of the cable. Another thing that will make an impact on the spinner calibration. The fluid is viscous. So the more viscosity of the fluid, also the more lag for the spinner to start rotating. So this distance from the time in which I start moving to, or the fluid start passing through the spinner until the spinner will start its rotation is what we call threshold velocity. And whenever we have wells, especially wells that are not producing with very high rates, this threshold velocity is going to be very important during the interpretation and during the spinner calibration. But if we have a well that is producing millions of standard cubic feet of gas, for example, or very high amount of barrels per day, then the threshold velocity becomes really, we don't really consider it that much in the interpretation, yeah? So you can see over here again, the same example that I showed you before. You have your zero flow region. So the points that you see in the previous slide, I could take them from this zero flow region. Then, if I want to trace my flowing line, I will take the points from this flowing region, yeah? So now, you see these points in blue, I took them from my readings in this flowing region, yeah? So I said, okay, my spinner rotating at 30 feet per minute. How many RPS I am seeing in my flowing region, yeah? Now, to select the regions, or what we call also calibration zones, we have to make sure that the spinner is constant, yeah? I cannot select a flowing calibration zone when the spinner is changing. Very important to select the calibration zones where the spinner is already constant. So then, what I do is that I will take my points and I will trace them, yeah? I will trace over here, okay, this is 30 feet per minute. How much is the spinner rotating? 60 feet per minute. This is the RPS with 60 feet per minute. And this is the RPS with 90 feet per minute, and so on. Now, the distance between my zero flow line and my flowing line is basically the fluid velocity. This is the velocity of the fluid in the wellbore, okay? And as you can see, the velocity of the threshold velocity is important. And this is important for the calibration when you do it by hand or you do it by software. But at the end of the day, graphically, the distance between the zero flow line that I trace with from the log compared to the flowing line that they trace also from the log, this distance is the fluid velocity, okay? So we can see over here, this is another way of putting it, velocity of the mixture is equal to the intercept in X plus threshold velocity, and the multiply by 0.83, but in this case, this is a generalization, this is a simplification of the mixture velocity from a spinner. This number is very common to appear in literature, especially in books that are old, but this is what we call the velocity profile correction factor. The interpretation softwares are taking the velocity profile correction factor based in Reynolds number, yeah? And as we saw, Reynolds number has several variables that we are also taking from measurements and from inputs. So in reality, you will not have always this 0.83. 0.83 is a legacy number, yeah? Saudi Arabia, yeah? During production logs in Saudi Arabia, very long time ago. And at the end, mixture velocity will be equal to velocity of the mix times the area, and the area we're getting it after calculating from the diameter measurement from the caliper. Now, there are some complications that will affect how the spinner will rotate. And the complication starts as your well starts becoming deviated. Why? Because as we see over here in the picture, we have over here an oil entry and we have water coming from the bottom, yeah? So the main body of water is coming upwards. But then the velocity, the oil starts segregating, okay? And as the oil starts segregating, we start getting that the oil velocity is going to increase due to buoyancy. And as the velocity of the oil starts to increase, some of the water is going to be displaced downwards. And this is what we call recirculation. Okay? We can see over here more clearly with numerical simulation. Okay? What you see over here in hold-up map represented over here oil hold-up basically. Oil hold-up is 0, is the blue color. And as the color becomes more hot, this is a higher oil hold-up, or this is the layer of oil basically. You can see that it's occupying the least amount of the pipe, yeah? You can see that mainly water is occupying the pipe in this case, yeah? In a 45-degree deviation. You can see over here in the velocity map that the oil velocity is very high while the water velocity is low and negative, okay? So we will have over here basically water recirculation, yeah? Of course, this water recirculation is going to be dependent on the, mainly on the velocity of the flow. It's going to be dependent on the heavy phase itself. The also is going to be dependent on the diameter of the pipe. So typically recirculation is going to be more obvious whenever you have large pipes, big size of pipe, and you have low velocity in the wellbore, yeah? In wells, for example, that have low production and you have a big casing, it is very common to see recirculation effect. Now, to complete the spinner application, so what the spinner is going to do for us in production logging, the spinner will be sensitive to any fluid entry. It will help us to determine a quantitative mass flow rate. We will use to be able to obtain the velocity of the mix, what we call multipass technique. As you can see over here, there is the log, okay? This is the production log, and you can see all my spinner passes merged into one log, yeah? I can see here my down passes and my up passes merged together, and you can see that the profile that the spinner response is repeating, yeah? It is very important as a quality control. My cable speeds have to be constant, and my velocity, my spinner profiles have to be repeating, yeah? So we can over here, this is a single phase well, and we can see over here, at the end, our output should be the velocity, the flow rate, yeah? This is what we need to obtain at the end of the interpretation. Now, we are going to look into a very important sensor also in production logging, which is the temperature. So we have over here what we call an RTD, and this is basically a sensor that is going to change its temperature, its resistance, based on temperature, okay? This is what an RTD is, okay? So whenever we look into a well, yeah, we will have what we call a geothermal gradient, okay? And any entry or exit of fluid, okay, is going to alter this geothermal gradient, okay? It's going to change the geothermal gradient. It's going to vary from the geothermal gradient. So for example, over here in the dotted line, I have the geothermal gradient, okay? And I see over here first entry of fluid, okay? Second entry of fluid and third entry of fluid. And I see that my temperature is separating from the geothermal gradient, okay? So for example, over here, I have here a fluid entry, okay? At the entry, okay, the temperature starts traveling upwards. If I don't see any other temperature, any other entry, fluid entry, my temperature tends to remain parallel to the geothermal gradient, and eventually it is going to come back to the geothermal gradient response after some time, as it loses heat. So this is just an example of a temperature log. It's just a diagram, okay? And we can see over here again how the temperature is separating from geothermal gradient, yeah, as we have any entry. Now, for example here, what are some examples of non-geothermal entries? Let's say I have channeling behind casing, especially if it is water. Temperature will increase from geothermal gradient. Let's say I have a gas entry. Initially, the temperature will decrease whenever I have the gas entry. Let's say there is high rock friction, okay? In this case, with the production. This tends to increase the temperature and away from the geothermal gradient. So these are just some examples, yeah? Over here, I have some examples again. So I have here an entry of water. I see my spinner is responding also to the entry of water, and my temperature is showing an increase. I have an entry of gas. Again, the spinner is responding to the entry of gas into the wellbore, but immediately after the gas enters into the wellbore, it happens expansion. And this is what we call the Joule-Thomson effect. And as it happens expansion, then we will have cooling effect. So you can see that you have a sharp decrease in temperature initially whenever you have a gas entry. Now we have here another example. Let's say I have channeling of water behind the casing. So over here my spinner is only indicating when the water already enters into the wellbore. But as you can see, the temperature is already increasing when the water enters into the channel. So this is one of the ways in which we can understand if there is channeling happening due to bad cement. In the case of gas, again, we have the same scenario, a channel below the perforation, and the gas is entering first into the channel. So I will see a first cooling effect as expansion of gas happens inside the channel, and then the gas enters into the wellbore, and I will see a second cooling effect. So again, we can understand here that I have gas flowing behind the casing, okay? So what are the temperature applications? The temperature applications is basically you use it for corrections of the sensors that are present on your production logging tool. You use them also for fluid conversions, okay? You require the downhole temperature data for that. You use it to analyze if there is presence of flow behind the pipe. Also, it can indicate what type of entry, which kind of fluid entry goes inside the wellbore, as we can see, where it's different from gas entering into the wellbore from water or liquid entering into the wellbore. And in some conditions, you could utilize temperature, deflection, to calculate mass flow rate. Yeah, but that's not a very simple, as it depends on many factors. But it can also be done. Okay, so now we will go now to the pressure sensor. So we can see over here a pressure gradient in a static well, yeah? Let's say we have segregation. So I will see in the wellbore oil gradient and a gas gradient, like in this example, or if there is water as well segregating, I could see in a wellbore gradient when the well is in a static condition corresponding to water. Okay, so the pressure will help me to understand changes as well in the condition of the well, yeah? When I put the well to flow, the pressure is also going to start changing, yeah? So it's going to start decreasing compared to the static condition. Another thing that we do is that we merge all the passes of temperature that we did during the production log, and we see if there is any variation of pressure every time I record a pass. I don't want to have any pressure variations when I'm doing my logging survey. I want that every time I do a pass up and down at different speeds, my pressure remains constant. Because if the pressure is changing, that is also indicating that the wellbore dynamics are changing. So my response from the spinner is not going to be really representative of what is happening downhole. So the pressure applications will be to understand the well is stable, understand if maybe I have leaks in the two tubulars, to understand the gradients in the wellbore in static condition due to segregation, to be able also to be an input for my fluid properties at downhole conditions. So it will be also an input to the interpretation, yeah? My interpretation software. And also we can understand some well operating parameters, like we can do production logging for testing. And in this case, we can understand bubble point pressure, and we can understand as well some factors. We can derive some factors such as permeability and skin. Okay, so we can do what we call multi-layer testing with production logging, which is an advanced type of application from production logging. Fine. Now, to enter into a well that is going to be producing multi-phase, we need to see some basic concepts. Okay? So, number one, hold-up. What is the hold-up? Hold-up is basically the area fraction of the pipe that will be occupied by a phase of interest at any particular point in time. Okay? Then, what is the water cut? The water cut is going to be a surface measurement, basically. So the water cut will be whenever I have my total production at surface, and I see what is the percentage of production of water from the total that I collected at surface. Okay, this is the water cut. So we should never confuse water hold up with water cut because they are completely different concepts. And it is very common that people will confuse them and try to and this will lead to misleading interpretation of the production logs. Then we have what we call superficial velocity. So superficial velocity is basically the velocity of a single phase flowing along in the pipe. Then we have the mean velocity, which will be basically the summation of all the superficial velocities, especially when we have multi-phase, we will not be having just a single phase flowing in the pipe. Now, very important, we will have the slip velocity or slippage velocity. And basically this is the difference between phases flowing together. So typically this is going to be the difference, yeah? So this is a very important, the slippage velocity is a very important concept. Then you have the single phase flow rate, which is going to be calculated by the average velocity times the area. And the multi-phase flow rate that is going to be phase velocity times the phase area, okay? And the phase area, as we mentioned, hold up is the area fraction occupied by the phase of interest in the pipe. So phase area is equal to the total area times the phase hold up. So again, water cut not equal to hold up, and again, percentage of water by volume produced at surface from a well. Hold up, as we can see in this diagram, yeah? So I see this diagram and I have water, oil, and gas flowing together. If I take just a slice from my well, downhole, from my pipe, I take a slice. I analyze this slice, okay? And then I see how much of this circle is occupied by water, how much is occupied by gas, and how much is occupied by oil, downhole. Then this is what we call gas hold up, oil hold up, and water hold up. In this particular example, we have that the oil hold up is 81%, the gas hold up is 4%, and the water hold up is 15%. Now, it's very important then to understand that water hold up plus oil hold up plus gas hold up is going to be equal to 1, okay? So 100%. And this is a downhole measurement. We should never confuse with surface measurement. Okay? Now, a slippage velocity, basically. A slippage velocity, the phase, different phases are going to be moving at different velocities. So typically the light phase will be moving faster than the heavy phase. due to density difference between these two phases. So for example, in this diagram, we can see that the velocity of oil is equal to the velocity of water plus the slippage velocity, okay? And if we actually apply our equations, we can see that the holdup of water is going to be equal to density of the mix minus density of oil divided by the density of water minus the density of oil, okay? The density of the mix is something that we are measuring. The density of the oil and the density of the water, downhole densities, is something that you get from PVT data, yeah, from customers. Now, slippage correlations, there are many slippage correlations and different type of flow regimes. And these slippage correlations were mainly derived by several people through experiments and empirical equations, okay? And basically over here, the determination of a slip, as we mentioned before, is going to be the difference of the velocity of phase, light phase minus the heavy phase. So for example here, if I have water and oil, the slippage velocity is going to be equal to the velocity of oil minus the velocity of water, okay? So to be able to get the velocity of oil and the velocity of water, we need to use the slippage correlations, okay? So you can see over here, holdup is also going to be affected by a slippage. So if there was no slippage, the velocity, the holdup of the heavy phase is going to be linearly dependent to the velocity of the mix. But in reality, this is not what happens due to a slippage. We don't have a linear relationship between the velocity of the mix and the holdup of the heavy phase, okay? So for example, if the oil is moving at a higher velocity than the water in a pipe, which is the phase that is expected to occupy more of this pipe, a higher percentage of this pipe? So in this case, the phase that is going to be occupying a higher percentage of the pipe is going to be the water, as the oil is flowing at a higher velocity. Okay, so this is just to show you a slippage velocity compared to density difference, okay? So this is also, we say that this is directly related to the density difference, but also it will be studied in flow loops. We will have another variations and contribution of conditions like the deviation, like flow rates. This is also very important whenever the slippage correlations are derived. So here we have an example of one of these slippage models, and this is what the Doppler model, yeah? So we have Doppler. Doppler model usually is used for gas and liquid. It's a gas and liquid slippage model. And we can see over here different type of flows considered by Doppler, yeah? We have over here the oil and water superficial velocity plotted against the gas superficial velocity. And depending on the velocity of every phase, you will have a different type of flow regime. For example, let's say that my velocity of the gas is low and my velocity of the oil and water is also low, then I will have what we call bubble flow. And this is the most easier to interpret. Let's say that now I have a relatively low gas velocity, okay? It's increasing, my gas velocity is increasing, sorry, and I have a relatively low water velocity. Then I can derive something called, I can get into my well, something called a slug flow. And when we have a well slugging, is one of the most challenging things that we might need to interpret with production logging. It's not going to be a straightforward interpretation. Then we might have a very high velocity of the gas and a very medium to high velocity of oil and water. And then we can start having something called mist flow, in which the bubble of gas are going to become very tiny. And this might become a challenge for some of our hold-up sensors. Now, another very common and very used model during interpretation, apart from Doppler, is Choquette. Choquette is basically an oil and water slippage model, yeah? Now, there are many correlations, same as I mentioned. This is just in this slide, I am showing several correlations existing by liquid and gas, and other correlations existing by liquid and liquid, yeah? And every interpretation software will have different correlations built in. And you will decide as well which is the best correlation that applies to a particular scenario that you have to interpret. Okay, so now we are going to go to the hold-up sensors. The first hold-up sensor that we are going to look into is what we call the Gradiomanometer tool. So what is a Gradiomanometer? A Gradiomanometer is basically a differential pressure sensor. Over here I have a diagram of the Gradiomanometer sensor, very simplified, very, very simplified. So in the middle of my Gradiomanometer sensor, this is where the sensor is going to be, my differential pressure sensor, okay? And I will have a bellow that will deflect with pressure, yeah? So in the bottom, I can see that in one side of my differential pressure sensor, I have pressure 2. And in the other side of my differential pressure sensor, I have pressure 1. And what I want is the differential between pressure 2 and pressure 1, okay? This is what my sensor is looking at, okay? Now, who is pressure 2? Pressure 2, now my sensor, just to complete, my sensor is connected to a pipe internally in the tool, yeah? And this pipe is filled by a special silicone oil, which we know its density. This density is known, okay? And this is just a special type of silicone oil. We cannot change it by another type, okay? It's just a particular type of silicone oil that we fill our tool with, okay? So then, who is pressure 2? Pressure 2, we have in our tool, we will have 2 ports that are going to be exposed to the wellbore, yeah? 2 openings in the tool exposed to the wellbore. So pressure 2 is going to be equal to the pressure in port A, okay, plus the column of fluid, okay? The column of fluid is given by density of the fluid in the wellbore times gravity times the height and cosine of the angle, yeah? Of the angle, in this case, this is a deviated well, yeah? Plus the delta P caused by the friction of the flow with the tool across the ports, okay? Then we have that pressure 1 is equal to the pressure in the port A, the top port, plus the density of the silicone oil, okay, this is pressure 1, times the gravity, times the height of the pipe that contains the silicone oil, cosine of the angle, okay, plus this is pressure in 1. So then, if I want to do my delta P, pressure in 2 minus pressure in 1, okay, I will end up that this will be given by the density of the fluid minus the density of the silicone oil multiplied by gravity, the height, okay, between the ports, cosine of the angle, plus the delta P due to friction. At the end of the day, what we want to obtain from the Gradiomanometer? What we want to obtain from the Gradiomanometer and that we will use for interpretation will be the density of the fluid in the wellbore, the density of the fluid that is around the tool. So in this case, the density of the fluid is going to be given by the density that is read by the tool minus the density due to the friction that we have with the delta P due to friction between the fluid and the tool, okay? So this is basically the density of fluid at the end, okay? This is just exactly the same, but put into another form, the equation. And there are the Gradiomanometer is going to be affected by several things that can happen to the Gradiomanometer measurement. It can be affected by jetting, something we call jetting effect. It can be affected by something called kinetic effect. And it can be affected by friction effect, okay? Now, G is going to change whenever the tool accelerates. So that's why we will have that this fluid dynamics can affect the final output of the Gradiomanometer tool that will be the wellbore fluid density value. Another thing is, let's say I have, for example, a very big amount of water and a very small amount of oil entering into the wellbore. At the end, this tool is giving me the total or the density of the wellbore fluid. So if I have a very small amount of one phase into a very big amount of the other phase, for example, very small amount of oil in a very big amount of water, the density that my tool is going to be reading is going to be very close to the downhole density of water. So if there is some error already in the measurement, the accuracy of the measurement is going to be low, okay? Another thing that will affect the accuracy of the Gradiomanometer tool is deviation. So as your well becomes more deviated, the accuracy of the Gradiomanometer tool is reduced. So at 62 degrees, the accuracy of the Gradiomanometer tool is reduced by half, okay? So typically, the Gradiomanometer is not the best tool to measure hold-up, to derive hold-up in highly deviated wells. This is just an example of jetting effect. So jetting effect happens whenever you have like a perforation that is producing with a very high rate, and you have one of the ports of your Gradiomanometer in front of this very high rate entry, yeah? So you basically derive a very high turbulence acting on one of the ports of your tool. So you will see a spike in your density measurement, yeah? You see over here a big spike on the density measurement. Then you might have the friction effect, and the friction effect, basically it is going to be caused by a suction due to the fluids moving across your tool, okay? And in this case, due to friction, your density is going to be reading slightly more than the true density of the fluid. But these effects, some of them you can correct for, because your tool will contain something called accelerometer. So some of these effects can be corrected by the accelerometer, and some other can be corrected as well by correlations, yeah? So now, what are the Gradiomanometer applications? You want to understand what is the density of the fluid in the wellbore, okay? You can identify entry of a light phase into a heavy phase, or the opposite, entry of a heavy phase into a light phase. Why? Because you will see a change on density, okay, wellbore fluid density. And at the end, the density of the mixture, you can use it to derive hold-up, okay? So, for example, I have over here, I have over here my Gradiomanometer density, and I have here water hold-up, okay, in the y-axis. I have here a point that corresponds to having 100% oil, okay? Now, in this point, I have 0 water hold-up because everything is oil. And the density that I am using to plot this point is the downhole density of oil. Who provides this downhole density of oil? This comes with the PLT data that my customer provided, okay? Then I have the density of water. My point, the yellow point, is basically 100% water point. Why? Because I have 100% water hold up, and this is the downhole density of water. Again, where this downhole density of water is coming from is coming again from PLT data, okay? If I know the salinity and I know the downhole density, the downhole temperature that I am actually measuring with my tools, I can derive what is the downhole density of water, yeah? Then the black point is basically what am I measuring? This density in pink is the density that I'm measuring with my tool, okay? If I actually intersect the line that I have between my 100% oil point and my 100% water point, I intercept it, okay, with the density that I am measuring with my tool, and then intercept this point with the y-axis. This is basically the hold-up of water in that particular depth. So I already calculated hold-up, so I will be able to understand how much rate of a particular phase I will be having from that perforation. Okay? Now, As I mentioned, sometimes we need more advanced hold-up sensors. So one of the advanced hold-up sensors that we have is what we call electrical probe. How this electrical probe is going to work? So basically, you see over here, there is the probe. You will have like a little needle in this probe, and you have the probe is actually attached to the tool. In the case of our tools, we will have 4 probes, okay, attached to the caliper of the spinner, okay, 4 probes, so you to have a good coverage of the casing, yeah. Now, how does it works? My tool is going to be conducting an electric current. Let's say I'm in water. If I'm in water and this is water saline, then this current is going to continue as a closed circuit, okay? Let's say a bubble of hydrocarbon comes to the probe. What will happen with the current that is being conducted? This is going to create an open circuit. So what I will be counting is the bubbles of hydrocarbon approaching the probe. Okay? In the case of hydrocarbon present in the wellbore, I have no current being conducted in my tool through my probe and the body of the tool. But let's say that a bubble of water comes into the ground of the probe and the tip of the probe. I will have then a closed circuit. So the idea is that to be able to determine the water holdup, I will calculate the amount of time that I have my tool in short circuit, my probe in short circuit, divided by the total time in which I am performing my measurement. So basically, I can count the bubbles of non-continuous phase, and I can derive directly a measurement of water holdup. Okay, so this is the idea of the electrical probe. So what are the benefits of this probe? So basically, that you can detect very small entries of non-continuous phase, but again, the only discrimination that you can do will be water from hydrocarbon. That will be the discrimination that this probe is going to do. At this point, this probe cannot tell you gas and oil. Yeah, it will tell you just water from hydrocarbon. Okay, so this is the other thing that is a benefit from these probes is that they are very close to the spinner measurement. So the closer your sensors together, the more representative that is going to be your measurement. Okay? Now, the next tool that you have for hold-up measurement is what we call the gas hold-up optical sensor tool. So this tool is going to based on optical principle. It's a what you can see over here in the screen is the probe. Also is going to be mounted in a centralizer. We are going to be having 4 of these probes. So to have a radial coverage of the casing, okay? And the tip is really very small. The sensing diameter is around 0.004 inch, okay? Very tiny needle that is going to be sensing. This is made of sapphire crystal, yeah? And is having the shape of a cone, in this case biconical, 2 cones, okay? You cannot really observe it here because it's really a very tiny, yeah? So now, what is the principle? The principle basically is related to optics, okay? So if I have, let's say I have, in this case, my tool is going to contain 2 items internally in the tool. It's going to contain what we call photodiode, and it's going to contain an LED, basically a lamp, a small lamp, okay, light source. These 2 are going to be connected to the probe, to the optical probe, the one that is actually facing the wellbore, by fiber optics. And what I'm going to be doing with the LED is that I'm going to be shining a light through the fiber optics, and this light is going to be present in the probe, okay? Now, depending on the type of fluid that is going to be around the probe, the amount of light that can be reflected back to the fiber optics and arrive to the photodiode. So if when we are in the presence of gas, the gas is having, in this case, a refractive index of 1.1, and the air having a refractive index of 1, okay? So if my light, if the light that is in the probe is the probe is around gas, I will have most of the light reflected back to my photodiode that is inside the tool through the fiber optic. If I am in water, less light is going to be reflected back to the photodiode, and if I am in oil, no light is going to be reflected back to the photodiode. So again, in this case, what we do with this tool is discriminate the presence of gas from liquid, okay? I want to see gas holdup compared to liquid holdup, okay? So how am I going to determine the gas holdup? The time that I have 100% of light coming back to my photodiode divided by the total time of my measurement, okay? This is what we call gas holdup. And this is, so now we have a measurement for water holdup and a measurement for gas holdup. And we have an equation that told us gas holdup plus water holdup plus oil holdup is equal to 1. So now I can sort for a multi-phase, three-phase condition if I want, yeah? If I have a well with the three-phase condition. Okay, this is just an example. So I have over here basically my optical tool can provide a waveform. Okay, this is raw signal of my optical tool, and I see in the waveform the point. Okay, the points in which liquid drops start basically hitting the probe. Yeah. So in Iraq, actually, they used at the time of the war, they lost a lot of information, okay? And they needed to understand or to have some estimation of the bubble point of the wells, okay? So what they did, this is an example of some of this work that was done in Iraq. They actually put the ghost and they see at which, basically, at which pressure did they start observing bubbles of liquid, okay? So you can see over here when you can start seeing bubbles, yeah, so that you start getting basically bubbles of gas, sorry. So you can start seeing the point at which your oil starts, at which pressure the oil starts liberating gas, yeah? At which pressure, and then they manage to estimate bubble point pressure, yeah? Now, we are going to go very quickly about what the interpretation software, what are the inputs, and what the interpretation software will give you as an output, yeah? So what are you going to require to make a good interpretation, PLT interpretation? You will require as much data as possible that you have from history of the well, okay? You want to have, for example, the production rates. You want to have production history. You would like to have cement bond logs to understand if the cement maybe is poor behind the casing. You want to have good PVT data, okay? Why? Because at the end of the day, it is not just about the log acquired, but you need to have a full scenario of what is happening with this well. You need to understand all the history of the well so you can do a better interpretation of your tool, okay? So let's say in the case of a well that is producing two-phase. So what will be the inputs? So number one, you are going to have a production logging program. Very important to understand what is the objective to achieve with this production log. Yeah, and when we see the objectives, is really to understand what are the entries from the perforations, or you want to identify a leak, or you want to identify a crossflow. You want to understand what is exactly the objective from this production log. You want to get as much well information as possible. Very important to get your production, your wellbore sketch and your completion sketch. If possible, you want to understand some reservoir information, yeah? Whenever you see a crossflow and you have some information from the reservoir, you can understand why the crossflow is looking like that, or why a particular zone is producing more than another zone. And of course, you want to have the PVT data, okay? So then you will acquire your logs. Your logging engineer will acquire the logs, and you as an interpreter and also the logging engineer are going to do a log quality control, okay? This is number one. once your log is having a good quality control, and normally the quality control, for example, myself, whenever the Schlumberger engineer is acquiring a log, I do the log quality control real time while the engineer is acquiring the log. Okay? So whenever he delivers the product, already we have a good quality control on the log, and I can tell him, for example, repeat a pass, or make a station, an extra station, and so on. Another thing we need for the interpretation model, my perforations and the calibration zones that I selected once I merged my spinner passes. I have to check if I have a zone with zero flow. If you did a static condition, if you did a static measurement, you will have zero flow, okay? Also, if in the case that you couldn't do a measurement while the well was static, you could consider sometimes the region below all your perforations, okay? Although this is not very ideal. Then you are going to build your calibration plot, okay? You build your calibration plot, and from there, you get your threshold and the slope of your calibration line. And once you do your calibration, you will derive, same as we saw in the spinner section, your velocity of the mix. So this is what the software is doing, yeah? And these are the steps, even if you do it by hand, with the help of Excel, these are the steps that you will follow. The next step, the selection of your slippage model, okay? The selection of the model choice. So the input from hold-up, okay? Do I have the hold-up tool is going to either give me, as we saw with the probes, a bubble count, or the Gradiomanometer is going to give me the density of the mix, okay? And from the bubble count and density of the mix, either of these two measurements, I will obtain hold-up, okay? Once I obtain hold-up, and I add the slippage velocity, okay? And notice that hold-up is an input also to slippage velocity, I will be able to obtain my downhole flow rates, okay? I already had velocity of the mix, okay? And of course, I have to do a quality control of my interpretation. And the quality control that we typically follow is that once we obtain from the interpretation our surface rates, if there is available measurement of the surface rates real time, we actually compare the surface rates that are being measured at wellhead with the surface rates that we are obtaining from the interpretation. And a good match is an indication that you have a good quality interpretation product, okay? And then if there is any discrepancy, you can investigate what is the reason that you have a difference between surface rates being measured at wellhead with the surface rates that you are getting from your interpretation. Okay, so this is with traditional production logging. Let's say now what happened in horizontal wells. What are the challenges when you have a horizontal well? So there are many challenges that you will find out whenever you deal with horizontal wells. You will have water that is going to be encroaching through fractures. You might have a stagnant water or a stagnant gas presence, cuttings, okay? Your pipe, your well is not going to be perfectly straight horizontal. You might have basically dips and increases on the deviation, okay? So it is very challenging environment for a production log. Not only that, once your well, you start increasing in deviation, your deviation increases, and near to horizontal, you will start getting fluid segregation, okay? So another thing that is going to be challenging, in a deviated well, highly deviated well, the method of conveyance of your tool is going to be different. To be able to drive the tool to the bottom of your logging interval, you will require either coil tubing, okay, or you will require a tractor. A tractor is a tool that drives your logging tools, okay, to the bottom log interval, okay? Now, I want to show you something. This is an example of how deviation will affect the flow. So you have over here in blue colored blue, these examples were obtained from something we call flow loop in our research center, yeah? And you can see in the example of 90 degrees deviation, you see that in this case, so perfectly horizontal well, you have that the velocity of the water is very similar to the velocity of the oil, okay? And you have a very nice stratification between the oil and the water in blue, the oil in red, okay? Now, if I have my well tilted at 88 degrees, who is occupying the most of the pipe? In this case, if I have my well going uphill. If my well is going uphill, as indicated in our experiments in the flow loop, the oil is going to be moving as a very thin layer on the top of the well at a very high velocity, and the water, as it is moving at a very slow velocity, is going to be occupying most of the pipe, most of the area of the pipe, okay? Now, let's say now my pipe is tilted downhill. As my pipe is tilted downhill, like in the 92 degrees case, we can see that the phase that is occupying most of the pipe, in this case, is going to be the oil. And the phase that is occupying the littlest area of the pipe is going to be the water. As it is a heavy phase, it's going to flow faster by gravity, okay? So the pipe is mainly occupied in this case or by oil, so that means that oil holdup is going to be higher than water holdup. So to be able to understand this type of segregation, we cannot measure that with a normal spinner. Why? Because the spinner will be affected either by the high moving oil or the slow moving water. It's not really going to give us a representative measurement from the flow in the wellbore, okay? Because it's going to be highly dependent on the type of phase that is going to be moving and how fast it's going to be moving. So in this case, we have another tool. This tool is what we call flow scan imager, okay? And this tool is going to contain mini spinners. These mini spinners are going to be located at different levels in the wellbore. And it's going to contain also at different levels of the wellbore. It's going to contain a water holdup measurement and a gas holdup measurement. So we'll be able to localize our measurements in the different segregations that we have in the wellbore. So this is a real-time information we get when we log this tool at different deviations. And you can see, for example, that at the 45 degrees, we say that these big circles are my mean spinners, and the white dots is the position of my holdup, water holdup and gas holdup sensors at different levels. And I can see at 45 degrees, I have a still sort of bubble flow, but I have my water suffering from recirculation, yeah? You can see the water moving down. Then if I am at the 90 degrees condition, I see that I have a nice segregation, and basically you can see that the phases moving to at the edges of the pipe are moving a little bit slower than whatever is moving at the center of the pipe. But I have a perfectly segregated phase. Now, the same examples as the flow loop that we just saw in the previous slide. Let's say the 92 degrees. 92 degrees downhill, we see that the water, the heavy phase, is moving faster, and the light phase, in this case gas, is moving slower and is occupying mainly the most of the area of the pipe. So gas holdup is bigger than oil holdup and water holdup, and this is real measurement, real time by our tool. So just to show you here, so you can see over here the spinner being a conventional spinner is going to be affected by whatever phase is flowing in the wellbore. But with this advanced tool, we can have a spinner located in the different points of segregation of fluids, yeah? So this is the idea of this advanced tool. Fine. Now that I show you or give you a taste of what is production logging, I will show you some examples of real logs. So we say that we can apply production logging also for diagnostic. In this case, this customer wanted to understand which gas lift mandrels are active. So to understand this, which tools do you think that we used to be able to understand which gas lift mandrels are active? So number one, we want to correlate, right? So to correlate, of course, we will need a gamma ray and a CCL, yeah? At least a CCL has to be there. Now, to understand if we have a change in the velocity of the flow, we will need a spinner. The spinner can indicate some change in the flow. But mainly, which are going to be the sensors that are going to be the most sensitive to an entry of gas? Temperature, because once there is an entry, we have a cooling effect. And pressure, density, because as I have a bigger entry of gas, my density is going to decrease. And the gas hold-up can also help us into this measurement. Yeah, if I have the gas hold-up probe, the optical probe, I could actually see the bubbles of gas entering into the wellbore. So if we look at the log, okay, first I have my completion sketch, very important in this kind of analysis, that I have a very nice description of my completion sketch against depth. If you are going to interpret, this is very basic, okay? You have to put it on your display. Second, I have my spinner. So I see that inside the tubing, in this case, the spinner is not rotating, okay? I see some spikes, but in reality, the choice of whoever did this log, they selected a full bore spinner, and typically the full bore spinner, unless you are using a turbine, is closed inside the tubing, okay? So to be able to pull out of the tubing. So we will not depend here in this particular log on the spinner 100%. Although we see some spikes in gas lift mandrel, in some of the gas lift mandrels, but these spikes are mainly due to the change of the caliper on the gas lift mandrel geometry, okay? But in this case, the spinner is actually closed. It's not rotating. So forget about the spinner. Then I will look at the temperature. So what is happening in gas lift mandrel number 4 and gas lift mandrel number 3? My temperature is just decreasing as I change depths, okay? But what happens in gas lift mandrel number 2? In gas lift mandrel number 2, I observe some slight cooling effect, okay? A slight change in temperature, drop in temperature. Then I continue to gas lift mandrel number 1, and I see a sharp decrease in temperature. Now, if I look at the Gradiomanometer, density mix, okay? The scale, notice that is from 0, the blue line, to 1.2. So I'm reading close to 1 across all the gas lift mandrels, number 4 and number 3, and the bottom in the wellbore. And then I see a drop in gas lift mandrel number 2, a drop in the density. So that means that something lighter is entering from gas lift mandrel number 2. Then I see a sharp change in gas lift mandrel number 1. So my density is dropping a lot and is getting closer to 0, yeah? And then I look at my gas hold-up measurement, at the image from my gas hold-up measurement. I see in red bubbles of gas. So my hold-up over here in red, this is gas entering into the wellbore. And then I see a very high amount of gas at the top whenever I have gas lift mandrel number 1, okay? And I don't see any other anomalies in the temperature. So I don't think there is any leak in the tubing, and I can know that gas lift mandrel 3 and 4 are not active, yeah? They are inactive. Only gas lift mandrel number 1 and gas lift mandrel number 2 are active. And gas lift mandrel number 1 is actually the one that has the highest injection seen in this completion. So this is one application of the production tools, okay? Now this is another application for the production tool. So this is basically to determine the entry of fluids from the perforations. So this is a two-phase condition, yeah? So we have over here in red, what you see in red, these are the perforation intervals, yeah? these tiny squares in red. What you see in yellow is what we call calibration zones. Calibration zones, okay? For what? For my spinner calibration, okay? I didn't plot here the cable velocity, but I have plotted all my spinner passes, yeah, at different cable speeds. When I plotted my sensors together, I could identify that my spinner is increasing only in some perforations, not in all of them, okay? So I see an increase in the most bottom perforation, okay? Now, this well, at the bottom of this well, there was a plug, and this plug is leaking. So I can see that water is already coming from the bottom, okay? Anyways, I see that my first contribution comes from apart from whatever is coming from the leak from the plug in the bottom, I see that my most bottom perforation is making the spinner increase. So I have here an entry of fluid, okay? Then I see the spinner remains constant until I go to this other perforation at around 13,050, okay? This one and the one above it are showing increase in the spinner. You can see that the one exactly at around 13,020 is showing the biggest spinner increase, okay? So we will think that this is the perforation that is contributing with most of the flow. Then I see that, again, my spinner remains constant, okay, across the other top perforations, meaning that these perforations are not contributing at all. So we have actually, in total, 1, 2, 3 perforations contributing in this well. The rest of the perforations are not contributing, are inactive. Then let's look at the wellbore fluid density. What is happening with the wellbore fluid density? First is close to 1, meaning that there is no hydrocarbon moving from bottom. Whatever is leaking from the plug is water, okay? How I know that it's water? My customer already told me what is the salinity of the water in this formation, okay? I already know the temperature because I'm measuring the temperature with my PLT string. So I also know, I already know the temperature. I also if I know the salinity and the temperature, I can determine what is the downhole density of water. And I compare with whatever my tool is reading, okay? So this is a quality control. Then I see that the density is dropping in front of this perforation that shows the first spinner movement. So what will that mean? If the density is dropping, that means that I don't have only water anymore. I have now presence of hydrocarbon entering to the system. Then I go to the next perforations, and I can see that now my drop of density is higher. So that means that I have more entry of light phase into the system, more hydrocarbon entry into the system, okay? When we do the interpretation, we do what we call, we obtain what we call apparent velocity from the spinner, yeah? So this is my velocity already. This is RPS. And once the spinner calibration is done, we will obtain the velocity of the mix. So this is basically the velocity of the mix. We have the density. So with the density of the mix and the downhole densities provided by the customer, we can obtain holdup of water, okay? And we have as well over here our electrical probe. Our electrical probe is giving us directly the measurement of water holdup, yeah? We can see that below all the perforations, water holdup is equal to 1. And we can see that the holdup, once we pass the 2 other perforations that are producing, it is around, the water holdup around, let's say around a third, yeah? And we see over here bubbles of hydrocarbon entering into the system, and mainly the hydrocarbon entering from the oil entering from these two perforations at around 13,050, yeah? So we have our water hold up and also the Gradiomanometer showing us the mixture fluid density. So the conclusion is, for this interpretation, we have water leaking from the breech plug. We have hydrocarbon also entering from the bottom perforation. And we have only hydrocarbon entering from the top, these two active perforations. So then you can take a decision of what you're going to do with this well. So what you will, if the cement is good behind the casing, something that you would like to do is basically to set another breech plug, and you will get rid of most of the water, yeah? Still, you want to evaluate if the hydrocarbon that you are getting from the most bottom perforation is economic for you, but let's say that I have no channeling behind casing. My well is producing just water coming from the breech plug and the water entering from this bottom interval, but the bottom interval is still producing hydrocarbon. So I will go and set another plug to be able to isolate that plug that is already leaking. Yeah, so I will reduce most of the water basically in this case. As you can see, the water holdup will be reduced. Yeah. Okay, so I will show you just another quick example of three-phase condition. So again, what we see over here is the gamma ray. To be able, at the left, the very left, we have the gamma ray. So to be able to put our log on depths, okay? We have in black the perforations. Then we have the CCL. We also use the CCL to put our log on depths as well. Then we have the caliper in green next to the CCL and blue. So we can see, for example, that in the casing color we have a different, the caliper is showing the difference, yeah? In front of the perforation also we can see that the caliper is increasing a little bit. And then we have the cable speed for this particular pass, yeah? Here is the cable speed in red. Then we see an image. This is an image of the water holdup. Water holdup measurement coming from who? Water holdup measurement coming from my electrical probe. So I can see, sorry, oops, I'm very sorry. For some reason, oops, okay, screen sharing has stopped. Why screen sharing has stopped? Share screen. Okay, share. Sorry, I pressed something by mistake. So you can see that the holdup is showing you a darker blue color wherever the water is the most. Also, you will see a green line next to it that says water holdup. Okay, this water holdup line is over there. Then you have the Gradiomanometer also indicating the wellbore fluid density, yeah, the density of the mix. So you can see that whenever the water holdup is decreasing, also the density read by the, or calculated by the Gradiomanometer is also decreasing. So what does that mean? That means that I have hydrocarbon entries. Below all my perforation, there was only water, yeah, below all the perforations. Then I see that from the bottom, starting from the bottom of my most bottom perforation, I have the spinner increases, okay? And I have as well the density decreases and the water holdup decrease. The image that you see in brown is bubble count. So basically, when the image starts getting darker, that means that you have a higher count of bubbles of the non-continuous phase. So basically, you have more bubbles of hydrocarbon entering into the system. So I can see something very important here. If I look at my top perforation is not active 100%. I have that only part of my top perforation is active. If I look at the track, again, why is disconnected? Fine. So what I was telling you, let me just expand this. Okay, this is fine. The spinner, which is this the red curve that is over here, you can see that the top perforation is only producing from a very small interval. And also you can see that most of the hydrocarbon coming from this part. Okay, how do I know that most of the hydrocarbon coming from that small part of the top perforation? Because I see that my water holdup decreases to the maximum. I can see that my density also decreases the most at this point. And I can see that the spinner as well increases the most to this point, yeah? So in this case, so for this particular interpretation, what was found out is that my top interval is producing mostly hydrocarbon. Okay, if you can see the percentage of water remains the same starting from the bottom perforation, yeah, from the very bottom and the bottom perforation. So there is no really input of water from the top perforation, but mainly from the bottom perforation itself. Yeah, you have some water entering into the system from the bottom perforation, and some hydrocarbon as well entering from the bottom perforation. But the top perforation is your main source of hydrocarbon, and only part of the top perforation. So what do you think could be a remedial in this well? I would say that maybe a remedial could be if we do a reservoir saturation log that can actually see the formation. If we still have behind perforation, top perforation, some oil presence, we could actually go ahead and reperforate, okay? And then we might be able to obtain a better production from the well. Now from the bottom entry, you know that we have just a very small amount of water entering from this perforation, yeah, producing 800 barrels of water compared to 150 barrels of oil. I mean, that will depend based on criteria that you have for your well, yeah, if you might want to isolate the bottom perforation or not. Well, so this is all from my presentation. I hope that it has been useful for you. And if we can go now to the question and answer section, please.
Thank you, Engineer Maria, for this enlightening session. Now we'll move to answering some questions we have here. Seems like our audience is very interested to know your start in your career in the oil and gas industry. Would you like to tell us more about that?
Yeah, so I am a mechanical engineer by career. I specialized basically in cars. I was supposed to work in the car manufacturing industry in my country, but I joined Schlumberger. I went through a recruiting in my university for Schlumberger, and I got selected as a field engineer. I started my career as a wireline field engineer in Egypt, and I worked in the field in Egypt for 4 years. And then I got transferred also as a field engineer to the south of Oman. And then after that, I left Oman after almost a year there. And I went to teach in the British Training Center in Scotland for 3 years and a half. Then after that, I went to Sudan as a what we call production services domain champion, which is the same position that I occupy right now. It's just that at that point, I was what we call a guest or a junior domain champion in Sudan. And now I am what we call senior 3. After senior, it becomes principal, and after principal, it becomes fellow. Okay, so I am now a senior 3 production services domain champion. And basically I advise regarding case hole logs in general, yeah, and perforation as well. This is about my career.
Wow, that's very impressive. Okay, moving on to the next question. Someone says, if velocity is an output and its measurement depends on Reynolds number, which has velocity as an input, then how is the parameter an output and an input in the same time?
Okay, so for Reynolds number, what we have as an input is the velocity, okay? The velocity will be an output from the calibration of the spinner, okay? What we need to derive the average velocity is what we call velocity profile correction factor. So how do we derive the velocity profile correction factor? First, we are going to obtain the velocity of the mix from the spinner calibration, okay? in which we convert the rotational spinner, the rotational velocity of the spinner into a linear velocity. So the velocity of the mix is what is going to be an input to be able to calculate the velocity profile correction factor, which is going to be dependent on the Reynolds number. Okay?
Okay. That's about it for the questions today. It was a pleasure having you, Engineer Maria Leticia Vazquez. Thank you for joining us. This was definitely a very insightful session. And thank you everyone for tuning in with us today. Engineer Maria, would love to have you back. Thanks again.
Welcome, and anytime if you have more questions, you can direct them to Ahmad, to Marwa, and I will be very pleased to answer any questions you might have.